When I say the word time, you probably think of clocks, calendars, and aging. You might think of time as something that just flows steadily, like a river. In physics, time is not that simple. It is part of the structure of the universe. It is woven together with space into what we call spacetime. In that sense, time is not just something we move through. It is part of the stage on which everything happens. And in modern cosmology, time also controls how gravity behaves, how the universe expands, and how the ultimate fate of everything will unfold. So if I ask, what if time is a weapon we cannot see? I am not suggesting a conscious weapon or an attack. I mean something more precise. I mean that the way time is built into the universe can act like a hidden mechanism. It can slowly but relentlessly change what is possible, what can exist, and how structures like galaxies, stars, and even atoms survive or fail. To understand this, I need to start with what we know about space-time. In Einstein's theory of general relativity, space and time are not separate. They form a four-dimensional geometry, 3 dimensions of space, 1 of time. Matter and energy tell this geometry how to curve. That curvature is what we experience as gravity. A planet orbits a star, not because it is pulled by an invisible force in the old Newtonian sense, but because it is following the straightest possible path in curved space-time. Time itself is part of that curvature. Time does not tick at the same rate everywhere. It depends on gravity and motion. Clocks near a massive object run slower than clocks far away. We have measured this with atomic clocks on Earth and in orbit. This is not philosophy. This is a tested fact. So already, time is not neutral. It behaves differently depending on the distribution of mass and energy. But the story becomes much more dramatic when we look at the universe as a whole. In cosmology, we describe the large-scale structure of space-time using solutions to Einstein's equations that assume the universe is, on average, homogeneous and isotropic. That means, on very large scales, it looks the same in every direction and at every location. The solution that fits this is called the Friedmann-Lemaitre-Robertson-Walker metric. It describes a universe whose spatial part can expand or contract as a function of cosmic time. That expansion is encoded in a quantity called the scale factor, usually written as AT. The T is time. How AT changes with time tells us how distances between galaxies evolve. We know the universe is expanding because of observations of galaxies and their light. In the 1920s, Edwin Hubble and others measured that distant galaxies are redshifted. Their light is stretched to longer wavelengths. The farther away a galaxy is, the larger its redshift. The simplest explanation is that space itself is expanding. As light travels through expanding space, its wavelength stretches. This is cosmological redshift. We measure it very precisely, and we can map how the expansion rate changes with time. We call the current expansion rate the Hubble constant, h-shrew. It has units of inverse time. That is already a clue. The expansion of space is not just about distance. It is about how distance changes with time. Now, if the universe contains matter, radiation, and possibly other components, the way the expansion changes with time is not arbitrary. It is governed by the Friedmann equations, which come from general relativity. These equations tell us how the scale factor AT evolves depending on the density of matter, radiation, curvature, and something else we discovered relatively recently: dark energy. When cosmologists first applied these equations, they expected that gravity from matter would slow down the expansion. Imagine you throw a ball upward. Gravity slows it down. The universe's expansion should be similar. It might expand forever but decelerate, or it might eventually recollapse depending on the total density. In the late 1990s, 2 independent teams measured distances to Type 1a supernovae in distant galaxies. These supernovae are useful because they are standardizable candles. Their intrinsic brightness is well understood, so by comparing how bright they appear to how bright they should be, we can infer their distances. When the teams plotted distance versus redshift, they found something unexpected. The distant supernovae were dimmer than they should be in a decelerating universe. The data showed that the expansion of the universe is not slowing down, it is speeding up. The universe is undergoing accelerated expansion. This was a shock. To explain it within general relativity, we need a component of energy with negative pressure that dominates the energy density of the universe at late times. We call this dark energy. Dark energy is not a poetic term. It is a placeholder for something we measure through its gravitational effect on spacetime. The simplest model is a cosmological constant, Lil, which Einstein originally introduced and later abandoned. In this model, dark energy has constant density in space and time, and an equation of state parameter W equals -1, meaning its pressure is negative and equal in magnitude to its energy density. This negative pressure causes spacetime to accelerate its expansion. We do not know what dark energy is at a fundamental level. It might be vacuum energy from quantum fields, it might be something else, but its effect is clear. Over time, as the universe expands, the density of normal matter and dark matter dilutes. The density of radiation dilutes even faster. The density of a cosmological constant does not dilute. So as time goes on, dark energy becomes more dominant. Time, through expansion, amplifies its relative importance. This is where the idea of time as a hidden weapon becomes interesting. Early in the universe, matter and radiation dominated. Gravity from matter slowed the expansion. Structures could form. Tiny fluctuations in density, seeded in the early universe, grew into galaxies, clusters, and the cosmic web we see today. Dark matter, which interacts gravitationally but not with light, played a key role in this process. It provided deep gravitational wells for gas to fall into, forming stars and galaxies. We infer dark matter from multiple lines of evidence. Galaxy rotation curves that remain too flat at large radii, gravitational lensing of background light by galaxy clusters, the pattern of temperature fluctuations in the cosmic microwave background, and the large-scale distribution of galaxies. All of these observations point to a non-luminous form of matter that makes up about 85% of the matter content of the universe. Dark energy and dark matter are very different. Dark matter clusters. It helps build structure. Dark energy does not seem to cluster on small scales. It acts smoothly, driving the expansion of space itself. In the past, dark matter's influence was stronger. In the future, dark energy's influence grows. Time changes the balance between these components. The same equations of general relativity applied at different cosmic times give different dominant behaviors. In that sense, time is not passive. It is the parameter along which the rules of the large-scale universe shift in practice, even if the underlying laws stay the same. Let me make this more concrete with a thought experiment. Imagine you live in a very young universe, say a few 100 million years after the Big Bang. The cosmic microwave background has cooled, but it is still much warmer than today. The universe is smaller. Matter density is high. Dark energy, if it exists as a cosmological constant, is present but negligible compared to matter. In that era, gravity from matter slows the expansion. Over time, slight overdensities grow. Galaxies start to form. If you could measure the expansion rate then and you knew only about matter and radiation, you might predict a decelerating universe forever. Now fast forward billions of years. The universe has expanded. Matter density has dropped because as space expands, the number of matter particles per unit volume decreases. But the density of dark energy has not dropped if it is a true cosmological constant. At some point, the density of dark energy becomes comparable to the density of matter. After that, it dominates. Once dark energy dominates, the expansion of the universe accelerates. The same initial conditions, the same physical laws, but at different times, the behavior of the universe changes from structure building to structure diluting. Time has revealed a new regime of the same equations. We see evidence of this transition in the data. The cosmic microwave background, measured by COBE, WMAP, and Planck, shows us the universe when it was about 380,000 years old. The pattern of temperature fluctuations encodes the relative amounts of matter, radiation, and dark energy. Combined with supernova data and large-scale structure surveys from projects like SDSS and DES, we infer that dark energy makes up about 68% of the total energy density of the current universe, dark matter about 27%, and normal matter about 5%. This is the standard LCDM model, a universe with a cosmological constant and cold dark matter. In this model, the future is controlled by dark energy. As time goes on, galaxies that are not gravitationally bound to us will recede faster and faster. Eventually, their light will be redshifted so much that it becomes undetectable. The observable universe, from our point of view, will appear to shrink in terms of what we can see, even though the actual universe continues to expand. Structures on the largest scales will be pulled apart by the accelerating expansion. Gravitationally bound systems like galaxies and galaxy clusters will remain bound because their internal gravity overcomes the expansion locally. But the space between these bound islands grows. In the far future, the universe becomes a collection of isolated gravitational islands in an ever emptier cosmic sea. If dark energy is exactly a cosmological constant, the expansion approaches an exponential behavior. The scale factor grows roughly like EHLT, where HL is a constant related to the dark energy density. This leads to what we call a heat death scenario. Over extremely long timescales, stars burn out, new star formation stops, black holes slowly evaporate through Hawking radiation, and matter itself may decay if protons are unstable. The universe approaches a state of maximum entropy, where no large-scale free energy gradients remain to drive complex processes. Time, in this picture, is the parameter that slowly erodes structure and complexity, not by an active attack, but by the relentless unfolding of thermodynamics and cosmic expansion under the influence of dark energy. But this relies on an assumption, that dark energy is constant in time. We do not actually know that. We measure its equation of state parameter W, and current observations are consistent with W equals -1, but with some uncertainty. If W is slightly different from -1, or if it changes with time, the future can be very different. If W on top -1, but still less than -1/3, we still get accelerated expansion, but with a different rate. If W evolves and approaches -1/3 or higher, dark energy could become less important in the future, and matter or something else could take over. If W -1 and stays below -1, we enter a regime called phantom energy. In that case, the energy density of dark energy increases with time as the universe expands. That leads to a big rip scenario, where the expansion becomes so violent that it eventually overcomes all binding forces, tearing apart galaxies, stars, planets, and even atoms at a finite time in the future. Phantom energy is speculative. It has theoretical problems, such as instabilities in quantum field theory. Most cosmologists are cautious about it. But observationally, we cannot yet rule out W slightly less than -1. So one of the open questions is dark energy truly a cosmological constant, or is it some dynamic field, often called quintessence, that changes with time? If it is dynamic, then time is not just revealing a fixed behavior. Time is actively moving the universe through different phases of dark energy dominance. That would make the long-term fate of the universe much more uncertain. Even if dark energy is constant, there is another way in which time shapes the universe like an invisible weapon. Think about gravitational structure formation. In the early universe, there is a competition between gravity pulling matter together and cosmic expansion pulling it apart. Dark matter halos form as gravity wins in certain regions. Gas falls into these halos, cools, and forms stars. Over time, galaxies merge, clusters assemble, and the cosmic web takes shape. But this process is time-sensitive. There is a window in cosmic time when conditions are right for galaxies and stars to form efficiently. If the expansion were much faster early on, structures would not have time to collapse. If dark energy had dominated too early, it would have stretched space so quickly that gravity could not gather matter into galaxies. In that sense, the timing of when dark energy becomes important is crucial. The fact that it becomes dominant only after large-scale structures have formed is not fully understood. This is called the cosmic coincidence problem. Why is the density of dark energy comparable to the density of matter right now when we are here to observe it, instead of being vastly larger or smaller at all times? We do not have a satisfying answer. Some argue that it may be an anthropic selection effect. Only in universes where dark energy becomes important, late do observers like us arise, because only then do galaxies and stars have time to form. Others look for deeper physical explanations, perhaps new symmetries or mechanisms that set the scale of dark energy. At present, this is an open area of research, but it highlights again how time, through the changing balance of energy components, controls what kinds of structures can form and when. Now let me connect this to gravity in a more subtle way. In general relativity, gravity is not just a force, it is geometry. The presence of energy and momentum curves space-time, but the way this curvature evolves is time-dependent. Consider gravitational waves. These are ripples in space-time that propagate at the speed of light, generated by accelerating masses, like merging black holes or neutron stars. LIGO and Virgo have detected these waves. They carry energy away from the system, and they stretch and squeeze space-time as they pass. The fact that we can detect these waves tells us that space-time is dynamic. It is not a static backdrop. It responds to events and evolves with time. On cosmic scales, the same is true. The curvature of space-time is not fixed. It changes as the universe expands and as the relative densities of matter, radiation, and dark energy change. The geometry of space at one time is not the same as the geometry at another time. This evolving geometry affects how light travels, how structures grow, and how we observe the universe. When we look at distant galaxies, we are looking back in time. The light we see left them billions of years ago, when the universe was younger and the expansion rate was different. To interpret what we see, we must reconstruct the time evolution of space-time. Cosmology is, in a sense, the science of reading the history of time written into the sky. Dark matter also interacts with this history. We do not know what dark matter is at the particle level. It could be weakly interacting massive particles, axions, or something more exotic. We know it interacts gravitationally. It clumps, it forms halos. It affects the motions of stars in galaxies and the bending of light around clusters. Over time, dark matter halos merge and grow. But in a universe with accelerating expansion, there is a limit to how much more structure can form in the future. Once dark energy dominates strongly, the expansion pulls regions apart faster than gravity can pull them together on large scales. Structure formation effectively freezes out. The cosmic web stops evolving significantly. The distribution of dark matter on the largest scales becomes fixed in co-moving coordinates. Time, through dark energy, shuts down the growth of large-scale structure. So if I think of time as a hidden weapon, I do not mean an attack from outside. I mean that the internal rules of space-time and energy, evolving with time, act like a one-way process that gradually reduces what can happen. Early on, the universe is dense, hot, and dynamic. Structures form, stars burn, complexity grows. Later, as expansion accelerates and free energy is used up, the range of possible structures and processes narrows. This is closely tied to the second law of thermodynamics. Entropy tends to increase with time in a closed system. The universe, as far as we know, is such a system on large scales. The arrow of time, defined by increasing entropy, aligns with the cosmic story of expansion and cooling. We do not fully understand why the early universe had such low entropy compared to what is possible. That is another deep question. But the trend is clear. With time, entropy rises. With time, dark energy dominates. With time, accessible structure declines. All of this is based on our current best model, CDM, and on general relativity. But we must be honest about what we do not know. We do not know the true nature of dark energy. We do not know the true nature of dark matter. We do not know if general relativity is exact on all scales or if it is an approximation that breaks down at very large distances or very high energies. There are alternative theories of gravity that try to explain cosmic acceleration without dark energy by modifying how gravity works on large scales. So far, these models struggle to match all the data as well as LCDM does, especially the detailed structure of the cosmic microwave background and large-scale structure. But the possibility remains that what we call dark energy is actually a sign that our theory of gravity is incomplete. We also face tensions within our current model. One example is the Hubble tension. Measurements of the Hubble constant from the early universe using the cosmic microwave background and LCDM give a value around 67 kilometers per second per megaparsec. Measurements from the late universe using supernovae and other distance ladders give a higher value, around 73. The difference is larger than the quoted uncertainties. This could be due to unknown systematics in the measurements. Or it could hint at new physics, perhaps involving dark energy that changes with time, or interactions between dark matter and dark energy, or something else entirely. If the Hubble tension reflects new physics, then our picture of how time, expansion, and energy density interact may need revision. Another open question is the ultimate fate of the universe. In a pure cosmological constant model, the answer is a cold, dilute, exponentially expanding universe, approaching heat death. In a phantom dark energy model, the answer is a big rip at a finite time, where even bound systems are torn apart. In dynamic dark energy models, the future could be more complex. Dark energy could decay, leading to a matter-dominated phase again. Or it could reverse sign, causing a future recollapse and a big crunch. Some speculative models even involve oscillations, with multiple cycles of expansion and contraction. At present, the data slightly favor a cosmological constant, but the uncertainties leave room for other possibilities. Time, in that sense, is an unknown tool in the hands of unknown physics. We are observing only a small slice of cosmic time. Extrapolating far into the future is risky. On smaller scales, like within galaxies and solar systems, time also plays a role in shaping structure through gravity and energy loss. Stars evolve over billions of years. They fuse hydrogen into helium, then heavier elements, changing their internal structure and brightness. Massive stars live fast and die young in supernova explosions that seed space with heavy elements. Low-mass stars burn slowly and can live for trillions of years. Over time, the stellar population of a galaxy changes. Star formation rates rise and fall. Gas is used up or expelled. Gravity, radiation, and feedback from stars and black holes interact in a complex way. This is not directly about dark energy, but it is another example of how time, combined with physical laws, acts like a filter. Not all configurations of matter are stable over long times. Some structures form, others decay. The universe explores possibilities, but time selects which structures can persist. Even black holes, which seem like the ultimate endpoints, are not eternal in our current understanding. Quantum field theory in curved spacetime predicts that black holes emit Hawking radiation. They lose mass and energy over extremely long timescales. A stellar mass black hole might take around 10 years to evaporate. A supermassive black hole might take up to 10 Sanger years or more. These times are far beyond the current age of the universe, which is about 1.38 times 10 years. But they are finite. Given enough time, black holes evaporate. Time, again, is the agent that allows quantum effects to accumulate and erase even the most extreme gravitational structures we know. So when I frame time as a weapon we cannot see, I am really describing the way the universe's own rules, applied over vast durations, erode structure, isolate regions, and drive the cosmos towards states where less and less can happen. It is not hostile. It is not intentional. It is simply the consequence of general relativity, quantum field theory, thermodynamics, and the observed components of the universe, especially dark energy and dark matter. We are used to thinking of forces like gravity as the main actors. But in cosmology, the time evolution of those forces and energy densities is just as important. The same gravitational law that builds galaxies in one era helps freeze them into isolated islands in another because time has changed the background conditions. There is a final layer to this that we do not yet fully understand: the origin and nature of time itself. In general relativity, time is a coordinate in spacetime and its flow is relative. In quantum mechanics, time usually appears as an external parameter, not an operator like position or momentum. In attempts to build a quantum theory of gravity, this mismatch becomes a serious problem. In some approaches, like the Wheeler-DeWitt equation, the fundamental description of the universe seems to be timeless. Time might emerge only in certain approximations or for certain observers.